Hello everyone. Welcome to the EasyPower Thursday webinar series. I'm your host today, Jim Chastain with EasyPower. We wanted to welcome everyone attending across the country and in some cases across other countries. Before we introduce our guest speakers for today, as we are in the habit of doing, we'd like to run a couple poll questions and would very much appreciate your participation and feedback. There's no obligation or liability, but it will help our presenters, our speakers, have a context for which the topic is focused. So if you would please respond in kind based upon your experience. That is, over time, how many projects that you've done have included relays. So this is mostly an average, and it's, as I say, there's no liability and no downside. It does give us a good perspective on the audience interest and level of knowledge. So it looks like we have a quorum here. We'll leave this open another 5 seconds. So here's how people have responded. Good. So our second question is, who is your go-to source for relays currently? Again, this is not to pry, it's just to kind of get a general feel for the audience's knowledge of the marketplace. Clearly, what we're have in line is a detailed background on relay operation and the evolution of the technology. And so there are several people in the field that are competent sources, and certainly this is to expand knowledge of the overall product line, not just lean it necessarily towards one vendor. Okay, looks like we got a quorum here. Good. That reflects at least my expectations. And then third, and this is one question I was really curious about, is how often do your projects involve electromechanical relays? And this is more history. And we're getting some good responses. So we do appreciate your participation and your attendance today. Looks like we have pretty much a quorum here. Thank you for joining in. Here's how folks have weighed in there. And surprises me a little bit. It's probably reflective of my lack of knowledge. Well, good. So at this point, I'd like to introduce our guest speakers, Andrew Legro and Nikita Mishra, and give me a couple seconds to share the screen. And Andrew, you have the podium.
Hello, everybody. This seminar is on protective relay basics, and it's kind of just as the title says, kind of a really high level survey of protective relaying. My name's Andrew Legro. I'm a field application engineer for ABB, and I work out of Florida, and my territory is Florida, and my job is basically to work with consultants and contractors and owners on applying ABB products and assisting them with power system design issues and things like that. So it's a really fun job. I'm kind of a jack of all trades because I represent and I provide assistance for the whole product line of that ABB sells for electrification in the U.S. and that includes General Electric. I came from the General Electric side when ABB acquired us in about 2018, it's about 3 years ago. So I got a pretty busy job, and it's a lot of fun. Our guest speaker, or my host speaker, is Nikita, and she's here to make sure I don't say anything dumb. She's the product expert on protective relaying, specifically numerical relaying, the real fancy stuff, the current day stuff. I'm an old guy, so I'm a generalist, and I go back to the days of electromechanical relay. So she's here to back me up. And Nikita, did you want to introduce yourself?
Thank you, Andrew, for sure. Hi, everyone. I'm Nikita Mishra. I'm a product specialist for the Western region for digital substation products at ABB. It mainly revolves around Reliant product line. And I have previous experience of designing low voltage and medium voltage switchgear. And I'm glad to be here. Welcome to the presentation.
Thanks, Nikita. I'll try to kick it off with just a little background. Like I said, I'm with the field applications team. We're about 60 strong, and we came from both the General Electric and ABB side. We're broken up into regions, so each FAE is in a region and is physically located there, as well as that's this job territory. So if anybody wants, please reach out to us, and we can put you in contact with your local FAE. And this team is for the U.S. and Canada. So any Canadian participants, we're pretty much the same group. I'm not sure. I don't really know outside the U.S. How ABB does it, but feel free to reach out to me. You'll have our contact information, email, if you need to get in touch with your local FAE. For those, I was kind of interested in those poll results because I was surprised, because it seems like we're going to have a lot more relay competent people on here than I was expecting. Maybe probably even more knowledgeable than me. The objective I had for this was more towards, my consultants tend to be low voltage consultants that get involved in relays on especially coordination on an infrequent basis, and they need a lot of support from me, and a lot of it has to do with just the basic concepts, because the fundamentals are the same, but all the verbiage and the technology and the terminology, it's just so foreign to people that deal in low voltage breakers and systems all day long, that I thought this was kind of a nice idea to try to expand out at least enough knowledge to be able to be comfortable having conversations and integrate some medium voltage relaying into your low voltage systems. So I was surprised that there seems to be a lot of experience on the call. So I kind of apologize. It's very high level, but I still think that you may be able to find it a interesting discussion. Just a little back on ABB/General Electric. They acquired us in 2018, so we're basically the combination of ABB and General Electric, and in terms of the protective relays, also Westinghouse, because ABB had acquired Westinghouse back in 1989, I believe. So when they did, they got the transmission distribution part of Westinghouse. So they got basically the utility segment, and then also the protective relaying segment. So all the old classic Westinghouse relays, like the COs, which I'll be talking about, we own them, and we still manufacture them, mostly for replacement. A lot of it's in new construction, but that's still a relay that we support from an engineering perspective. So our history, our group, the combined ABB, Westinghouse, and now even the GE, we don't have the GE line of relays. GE Multilin was left behind with the GE Power Grids business, so they're a separate company, and they have their own expertise going back 100 years, and we have some of that because we brought some of those guys along with the acquisition. So the point I'm trying to get across is that ABB, from a protective relaying perspective, goes back all the way to the turn of the century and the beginning of electrification. So after the acquisition of Westinghouse, ABB basically took the electromechanical relay and then moved it into the 21st century with first electronic, and then then straight into multifunction numerical protective relaying. So it was a rocket ride from where they started. But so we've been around as a company for a long time, even though you may not know our name in North America so well. Like I said, the objective is to try to do a really high level survey of protective relaying. And I kind of said it's geared a little bit towards the low voltage guy that's familiar with using EasyPower for coordination studies and for low voltage breakers, but maybe has to get involved in some relay projects. The fundamentals I'm going to talk to are going to use electromechanical relays kind of as a baseline, because if you're familiar with it, all these terms like the names of different curves and the concepts of like tap and time dial, they all go back to the electromechanical relay, but they've been essentially brought forward into the world of the numerical relay, the electronic, microprocessor-based multifunction technobox. And if you're a younger person and you just you started to experience and learn about relays from, say, about 20 years ago, a lot of the terms don't make any sense, and they don't, because they don't really have a direct analog into the numerical relay. So that's kind of the basis. I'm gonna try to get just the basics of it, and then sort of relate them back to what the equivalent term would be for the low voltage world, the world of trip units and molded case breakers. And that brings me, gives a good segue into the relay versus the low voltage breaker. So basically, relays are pretty much exclusively used on medium and high voltage equipment. And there's always some exceptions. And general note is I'll be making a lot of statements in this that some of you experts out there will be upset about or disagree with, and that's fine, because it's the whole topic's kind of an art and a science. So everyone's coming from their own different perspective and training, and so there may be some controversial things I say. And it's my opinion only, not ABB's. But feel free to shoot me emails if you want to discuss things I say, or you think you think that something I said was wrong or whatnot. But so the relay versus circuit breaker, relay medium voltage, the molded case circuit breaker, and low voltage circuit breaker for under 600 volt applications. The big difference is that the relay is a one component in a larger engineered system, whereas the low voltage breaker is a all-in-one solution, basically pre-engineered. It's I don't like to say plug and play, because there's still a lot of engineering goes into it, but it's a solution that you pick up your breaker, and then all its ratings and everything are pretty much predefined, and all the parts you need are included in the package that you buy. Whereas a relay it provides only the smarts for the system. It's only the protective functions and maybe some logic for control, maybe metering, but it's not the circuit breaker, and it's not even the sensors. And the circuit breakers and the sensor and the breaker mechanism in a low voltage breaker all come together as one big package. So the relay requires sensors, which is typically current transformers, control power. That's another important thing. They're not self-powered. You need to have some sort of reliable power source, battery or UPS, in order just to have the protection system work at all. And then the circuit breaker itself. Historically, they started out as sort of clockwork devices using induction disks and electromagnets. But now, obviously, they've developed into these full-blown supercomputers in a box. So a lot of evolution, and most of that evolution took place only in the last, I would say, 25 years. I had some information from FP&L, local utility down here, and they basically said that they were fully electromechanical until the mid 1990s. Now they've almost made a complete transition, but the big push didn't come until very end of the 20th century. So it went from 100-year-old technology to state of the art in a very short period of time. A relaying system requires a bunch of engineering, obviously, because you have multiple components and they all have to be, they all have to work together as a system. And it's the responsibility of the specifying engineer and design engineer to make sure that his relay and his CTs and his breaker are all working together as a system, and to know what the totality of those components can do performance-wise. Whereas the low voltage breaker, it's going to be printed in a data sheet exactly what that breaker can do in terms of its curve. The curve includes all the trip and total clear times, and so it's a package versus a system. Here's real basic stuff. The difference in symbology between describing a medium voltage system and a low voltage system / circuit breaker. The medium voltage, the standard ANSI stuff is sort of this box symbol for the breaker versus this air circuit breaker symbols conventionally used for low voltage like molded case stuff. And molded case and power circuit breakers. The CT is the symbol here, and then the relay. But there's a unique utilization of these ANSI device codes for relaying, for medium voltage stuff, that don't necessarily convert over to or are used in the low voltage. So in other words, you would define these two numbers, 50, 51, are instantaneous and time overcurrent protection as defined in the standard. The device 52 is the actual circuit breaker itself. This 205 is just the ratio of a CT. And then the equivalent for a low voltage circuit breaker is its trip characteristics. In this case, it's electronics, so it's LSI, long, short, instantaneous, and then it's sensor and frame ratio, 200 amp trip or 200 amp sensor plug, and then 600 amp frame. The LSI would roughly equal, the LS would be the 50. I'm sorry, the LS would be the 51 device, and the I or instantaneous would be the 50. So 50 is instantaneous, 51 is time overcurrent. Yeah, this is actually an important slide because this goes through one of the kind of big things I'm trying to convey on this presentation is this terminology. Like for a protective relay, the settings are called like tap, time dial. They use the term range, curve type, inverseness of a curve, CT ratio. Equivalently in the low voltage world, you'd have things called like pickup, delay, long time, short time, instantaneous, ground. The CTs in a breaker like this are called sensors. So completely different vocabulary, but both describing exactly the same physical phenomenon and basic kind of components, but completely different vocabulary. Here's just a kind of a breakdown of the device numbers, the ANSI IEEE standard device numbers. And these are not only valid for the circuit breaker, switchgear world, but also the control. So if you're designing a motor control center, schematic, you would use the same device numbers. So they're sort of universally used in the power control realm of engineering. Here's a very abbreviated list. The total list is this IEEE standard, and we have our own. I know ABB has a couple really nice printouts of descriptions of all the device numbers and what they do. If you shoot me an email, I can send you a copy of that. And the device numbers basically go from 1 to 99. So this is just a very, very shortened list of kind of the high points of if you're a casual user of relays, what you got to know. And really the big ones are device 52, which is the actual circuit breaker, device 51, which is your time delayed overcurrent, and then your device 50, which is your instantaneous overcurrent. And then I'll get to the next slide. It can be broken down even further into whether it's instantaneous for a phase, instantaneous for a neutral, 51's time. So this would be a time overcurrent for a neutral, time overcurrent for a ground. And then you have some the rest of these are sort of non-overcurrent protective type functions. Overvoltage, 81's frequency. 86 is a pretty important one. It's a lockout. 87 differential protection. So in my opinion, about 90% of the time, the devices you're going to see are kind of in this list. So then there's some common suffixes that are used on those devices, and it's like P for phase. So you'd have a 51 time overcurrent with a P means the phase, N for neutral, G for ground, B for bus. There's a typo here. I should say 87B as in boy. T for transformer. That's 87T, transformer differential. BF would be breaker failure. And usually when we get into the numerical relays, these are going to be important because each element in the numerical relay will say that it's a 51P or a 51N. And that terminology even shows up within EasyPower itself when you select a specific relay. You know, it might be a ABB REF 615, and the actual library is for the neutral protection, so it'd be a 51N. So these are kind of the important ones to know. Fundamental, the basic parts we kind of already discussed are the relay itself. This is an example of a ABB numerical relay, current transformer, and circuit breaker. So you need at least these three pieces to make a complete circuit breaker system. And this circuit breaker, this is a vacuum breaker used for medium voltage switchgear, but it could be a whole slew of different kind of breaker technologies and sizes and configurations, but it's just kind of like this more of a medium voltage metal clad switchgear example. Even the current transformer, people with a sharp eye will realize that this guy here is it's a 600 volt class CT, but it's used in 15 kV switchgear because it goes around insulating bushings. So this is the actual class of CT that we would use in our medium voltage switchgear lineups. Here's a slide just kind of showing the physical device in relationship to some of the symbols used. So these two circles that show a instantaneous time overcurrent and then a time overcurrent ground. All these elements are part of this single box, plus a whole slew of additional stuff. CT, here's the actual CT. Ratio would be, this one was 600 to 5. The 5 on the secondary is a typical secondary for, it was historically a default standard secondary CT current in North America. So every CT was something to 5 in North America. Now, if you go into the European market, they had a lot more of the X to 1 ratio. So they used 1 as a secondary current versus 5 in North America. And the 5 goes back again to the fact that they were electromechanical relays, which drew physical load off the CT. So the standardizing on 5 amp gave them a little more power capacity, so they could drive the actual elements that make up the relay. That's just a little background. And this last number is a accuracy class for the CT. And then here's your circuit breaker. Same stuff. This is all pretty much medium voltage gear. And then here's your components that make up one breaker, and then they all go into in some cases a bigger assembly. So this is all those components brought into a really short lineup of medium voltage metal clad gear. And this is a double stack, so this is actually 4 breakers, 2 on top, 2 on the bottom. And then all your instrumentation is in the center section. So you see you got a relay that might be for the top. This one might be for the bottom. Trip and close handle for the breaker. Same thing over here, just one relay. So one of these might actually be an empty cell, I'm not sure. But basically it's saying that these components all pop into one of these cells, and then they make up a bigger system like switchgear. The CT is a big part of designing a protective relaying system, because it really sets the size of the circuit you're going to protect. In the medium voltage world, the first circuit breaker frames, there's not as much variation. So you may have a 600 amp, 1200 amp, 3000 amp frame, and that's it. So you set the current for the specific circuit you're trying to protect based on that CT ratio. Let's see here. We talked about this. The typical secondary is a 5 amp. The primary side is the one that's connected to the actual cable or circuit. The secondary side is connected to the relay. This is interesting. This interesting point. Multiple relays can use the same CT. So you can have one CT drive a couple different protective relays plus a meter. The limit is defined by how much physical load that CT can drive, and then that is relative to the accuracy class of the CT, and that gets a little complicated. But the larger that class is, and it's usually like a C something, like C100 or C200 or C50, that C accuracy class basically is equivalent to how much electrical load the CT can drive and remain accurate, remain out of saturation. So and it's sort of like terminal voltage. So if you have a C100, well, I think I have an example here. Let's see. So your accuracy class, going back to that point of how much it can drive, say you had a C, and most of them are usually classified as C. That's a I can get into that, but the terminal voltage part of it. So if it's a C100, it can drive 100 volts of load without saturating. So you can basically, because it's CT normally CT is shorted, obviously, but then whatever load it's driving through its short, whatever voltage develops there, that would be this number. And this is not, it's not an exact correct explanation of what I'm saying, but it's sort of indicative. So basically the higher the number, the higher the C class, the more load in terms of protective relays that CT can drive. So that was a little bit contrived, but let's see if I can clean up a little bit. Yeah, back to the ratio, the first part of the ratio, like for example, the 600 here, means that the 600 amps of line current will produce a 5 amp secondary current in the CT. Oh, here's an interesting note. There's two basic classes of current transformers. One's for metering. So there's a metering class, and then there's a relaying class. Don't use metering class relays metering class CTs for protective relaying applications. They're not designed for that. They're designed to be accurate, but they're not designed to have a large range on them. So when you do a relaying application, you're going to select a relaying class CT. Now you can, in the inverse to that, you can take a relaying class C, can be used for metering, but you may have some reduction in accuracy. So kind of the bottom line, and I'm going to move off the CTs as fast as I can because this just gets too deep. But from a protection engineer standpoint, the most important things to know about the CT are the ratio and the accuracy class. I'll try to go through some of this quickly. Here's a table of some standard CT ratios. These are for multi-tap CTs, so you can get a CT that you can reconfigure its ratio based on what taps and jumpers you put on it. So you can get a 600 to 5 MR, would be multi-ratio, and that can be set to drive either a 50 amp load or a 600 amp load, and all these variations in between. Here's some stuff about circuit breakers. The big takeaway is that the circuit breaker has no inherent protection on it. It's just a switching device capable of interrupting short circuits and operating also as a switch. But it's got no brain in it. Basically, mostly no sensors, because usually the CTs are this is a draw out breaker, so the CTs are part of the switch gear or the assembly it goes into. So it's just the breaker itself, as opposed to low voltage equipment where the breaker's a one piece does it all, plug and play. If you're a protection engineer, the basics you need to know are the frame size, and this pretty typical frame size is 600 to 3000 for 15 kV class gear. That's it. So if you needed a 100 amp breaker, for 100 amp application, the smallest you can get is a 600. And actually, in medium voltage gear, we bought them out at 1200. So if it's a 100 or a 200 amp breaker, you're in a 1200 amp frame. And all the actual where it trips at is set by the CT and the relay. The interrupting values are good to know. Now they're all done in KA, just like low voltage. It used to be a different system, but it's changed over the years and got a little bit simpler. Typically, they interrupt in either 3 or 5 cycle. It was historically 5 cycle was pretty common, but now I think that the 3 cycle breaker is a little bit more common and pretty readily available. And this is important because this determines how fast you have to add this time onto the time it takes for the relay to pick up. And we'll kind of get into that. And then you should also know what the actual trip coil voltage of the breaker is. And note that the trip coil voltage doesn't have to be the same voltage as the any other control in the circuit breaker, like the spring charging mechanism. For example, you tend to want to do your trip coils at DC. So you might have a 48 volt DC trip coil, but then the rest of the system that charges the spring charging motor and it does your control and contacts, some of that might be 120 volt AC. So you can easily have mixed voltages in a circuit breaker. It's just something you need to be aware of. Now we're finally getting to the overcurrent relays. Basically, I'm just going to go through. There's many types of relays, do all kind of different protection functions, but I'm keeping it really simple. It's just an overcurrent device. And so this would be your 50, 51, 50 being instantaneous, and 51 being your time overcurrent. Here's an example of, again, the same multifunction relay, but in the next couple slides, I'm going to start out with the electromechanical and then kind of move my way up into numerical, like, multifunction. This here is your overcurrent relay, electromechanical type. This is a ABB CO9. This goes back for many years ago. It was probably in production for maybe 80 years, this thing. This started out as a Westinghouse product, and then when ABB acquired it, it's ABB. But so you might see some old equipment in there with the Westinghouse nameplate or the ABB nameplate. It's the same relay. We own it, and contact us for information that you need on it. The electromechanical relays they're kind of clockwork-like devices, and they tended to be in the medium voltage world because they were more accurate, and it was more things you could do with them in terms of protection, as opposed to stuff that was in utilization equipment at low voltage. So the electromechanicals used induction disks and solenoids and things like that to achieve the protective function, whereas the circuit breaker at low voltage used thermal heaters or just thermal elements plus some magnetic stuff. But that was sort of the origins of it. Now that's all changed, and current day there's no real in my mind, there's no real difference in the accuracy you can get between a low voltage circuit breaker with an electronic trip unit and a high-end relay. So they kind of started out in two different directions for two different applications, but now they're very much overlapped in what you can do with them. But this last point's kind of good. I know there's a lot of these that still are in service, so I sort of expect that, you know, some of you are going to get applications where you're going to put, you know, a new system on where you're going to utilize multifunction relays, but you got somewhere you got to coordinate it with an old induction disk. So hopefully this will kind of help you out, because these have been around for a long time and they're not going anywhere. Here's just kind of a comparison and form factor. These two relays are about the same dimensions. This might be a little bit bigger, but you can see there was a lot of intentional design on this to make it mimic this relay, because one of the interesting features is the internals of this relay are draw out. You can open this box, pull out this relay so it can be tested. Same thing here. This is a handle that pops out. So the back part stays within the gear, but you can draw this relay out, test it on a bench, or even just swap it out if you know if you had a problem with it. So it's this is just a follow through on the original concept, because it worked. This was a good design. It worked well, and it was copied over and brought forward into the new technology. But this relay here can do overcurrent 5150 on a single phase. That's it. So on a normal three-phase breaker, you'd have one of these for each phase, A, B, and C. This guy, all three phases, plus almost any other thing you can ask it to do. So a panel that might have had 4 or sometimes even like 6 or 9 of these devices on it for one breaker has now been reduced to a single box. Here's a nice slide just showing you this is the internal component. This is the actual relay itself that's been drawn out of the box. This is kind of a bad picture, but you can see this is a overcurrent relay with and I'll get into some more of the details, but this is the internal of that. The relay, I'll get through this real quick, but basically the overcurrent relay uses an induction disk to time itself for the time overcurrent portion of the protection. And there's 2 basic settings for an induction disk time overcurrent. There's the time dial, which sets the delay, and there's the tap, which sets the pickup. That's it. Now you get into your multifunction relays and things start to get really complicated, but if you go back to the basics, 2 settings, time dial, tap. So just as sort of a quick tutorial on how to read these things. They look complicated, and if you walk up to it, it's very unclear as to what they're set to, what they do. So I just want to do a really quick thing on how to look at an old electromechanical relay and see what the settings are. For the overcurrent, time overcurrent, there's a tap and a time dial. The tap is literally a tap. It's little holes with a screw element that you can change from all these predetermined tap values, and that will set the pickup of the relay. And the time dial is literally just a little dial, and no notches, no detents. It's a continuous dial that goes from, like, say 0.5 to 11, and you spin it until it meets the setting. That's it. This relay, the CO, also has instantaneous or 50 protection on it too, and that's kind of just a separate element contained in the relay right here. And its settings are really simple too. You have a range tap, which is the same as the other tap. It's a screw that screws into whatever hole you pick. And then there's a pickup adjustment dial. That's all there is to it. And then this piece here would be a flag that drops if it picked up on that. But the point I'm getting across is that for an electromechanical overcurrent relay, you had 51 tap, 51 time dial, and then 50 pickup with maybe a range. Sometimes there weren't even ranges on them, depending on the model. This is the last piece. This is just it's an extra contact, but I noted it because it also contains a trip flag. So the relay actually has two trip flags, one for the time overcurrent element, which is here, and then one for the instantaneous. So in this picture here, you can see that this breaker had tripped on, or this relay had tripped on time overcurrent. Here's an example of kind of what I was talking about before, where you have multiple relays required for the protection of a single circuit breaker. This was pretty typical. This is old GE gear, I think power brake. So these are probably GE relays too, circa 1980 probably. But you can see that here's kind of a three-line diagram. You can see this one breaker, and this is the pretty much the most basic overcurrent protection you can put on it, had a 3 relays for phase overcurrent and 1 relay for ground overcurrent. So 4 relays in total with all the associated wiring just for one breaker. Here's some explanations on the settings of the relay. We have it's back to what I was talking about: tap, time dial, and then curve. So this is for time overcurrent. So if you're a time overcurrent, you have your time dial, which essentially moves the curve up and down in time on the time axis, and then your tap, which essentially moves the pickup left and right on your ampere axis. Your 51, or your 50 is then this part of the curve down here, and that typically only has a pickup value. It may have a range that's set plus the pickup value, but as you have increasing pickup, that moves this part of the curve to the left or the right in terms of amps. And all this stuff carries forward into the numerical relay. So, with all the same terminology. One of the advances that almost all, I think, numerical relays have now is they have this added piece that you can add to a typical overcurrent, which is sort of a time delayed element. It's sort of a time delayed instantaneous. Some people call it a 50 TD, but it allows you to have a true instantaneous plus a delayed instantaneous, and then a time overcurrent, which is inverse time. And these set with pickup and then a pickup or tap, and then delay. And this lets you mimic some of the features that you would see in like a electronic low voltage breaker, where you'd have a short time element, a long time element, a short time element, and then instantaneous. Here's the curve family that's pretty typical for relays. There were all these model numbers dependent upon which manufacturer you had. ABB/Westinghouse had, they called them CO, and then gave them a number at the end. GE was IAC with a number, but then they had these terms called like extremely inverse, very inverse, inverse, moderately inverse. The terms are sort of what the curve is, but they're not consistent across manufacturers. Now there's some standardized versions of it. So there's an ANSI standard inverse and extremely inverse, but there's also the CO inverse and the IAC inverse, and those are different. And probably in modern days, you really only have to worry about CO11 through CO8, extremely inverse through inverse. The rest of them, except for definite time, the long and the short and moderately are kind of legacy curves. But you can see that as that curve type changes, its response changes. So you can see that like a CO11 is its inverseness, so to speak, gives it more of a I squared T response, and then a very inverse is a little bit less than an I squared T and more of a thermal overload type response. So these are usually the basic selections you have for curves when you're doing the protective coordination study. Here's an explanation of the last important one, which is definite time. And it used to be that definite time, it wasn't really definite time means that if the relay picks up, it times to a certain preset number, and then it trips. The historical stuff and some stuff that's still around there today, is not exactly, it's more this red curve than it would be the on-off. So just be wary of that. And so the definite time is used for things like that 51 time delay, a lot of functions that are not involved with current, like over voltage. It's basically hit a pickup value, wait a certain amount of time, preset time, and then trip or not trip. Here's an example of the time dial adjustment, and this is basically to show, this is a CO9, this is a very inverse curve, and here are the different time dial settings. And it's really meant to illustrate that it's not, in relays, it's not a true up and down change in time. It's more of a slope to the left and right. So as you increase the time dial, the slope is actually moving up, but it's also moving a little bit to the right in terms of amps. So the curve, the way the curve looks, kind of changes. And that's a little bit different than the way low voltage breakers with electronic trips work. Try to wrap it up here. Just the importance of this one's kind of important, so I'll go through it. The relay and the curves that get represented in EasyPower and standardized, it's just the response to the relay, but it doesn't include what the breaker's doing. So this blue line is the relay, and then I drew in this light blue hatched area would be the additional time that you need to be wary of to allow for the breaker to pick up, trip, and clear. And that ranges, and this also includes some of the accuracy of the CT, plus artifacts of the relay itself, like Electromechanicals had an over travel where they sort of spin down. So all those factors had to get added into the relay curve response so that you knew where you could set your next breaker. So your next breaker couldn't be anywhere except above here, or else you wouldn't be fully coordinated. So in other words, you couldn't just draw the next breaker's curve right down this area, intersecting this hatch, because you would run the possibility of tripping both of them at the same time. They wouldn't be coordinated. And here's a couple really, really rough recommended intervals. If you're looking at a electromechanical relay, if you didn't have detailed information, a safe number to use in terms of time to interval time between devices was about 0.4 seconds. For a numerical relay, you can cut that at least in half to 0.2, and most of the times you can go much lower than that to probably no more than no less than 0.1 second or 6 cycles. That's probably cutting it to the bone. But you can get tighter coordination as long as you put the work in of doing the engineering analysis, because there's a lot to it. So that's one of the big things that is different between doing relay coordination versus low voltage breaker coordination. Just kind of further example. Here's a downstream relay and an upstream relay, and I'm just kind of showing electromechanical. And I'm just showing you that's that minimum value you got to set where your upstream relay is away from your lower relay, and that's all due to the speed of the breaker and the accuracy of CTs and a whole myriad of design issues. Since we're running out of time, I'm going to speed through some of that stuff and just get down to some basic recommendations for electromechanical relays. I think I've been through this. The various manufacturers all had different curves with the same name. So there may have been like a CO9 very inverse from ABB, wasn't the same curve as what GE called a very inverse, which would have been an IEC 53. So the take home is, if you're in an electromechanical world, avoid mixing different manufacturers and models, because they're not. It can be done, but it makes your life more difficult because they're not the same type curves. Most of you probably won't get into that situation anymore because you're not speccing new electromechanical relays. For multifunction numerical relays, doesn't matter, because most all relays have a whole selection of different curves you can pick. So they'll have ANSI standard curves and IEC standard curves. The only thing to remember is whatever you're picking, do the same thing. So if you're going to do ANSI, make sure all your curves that you use in various relays are all ANSI, and you're good to go. And I would choose ANSI standard curves for applications in North America. There's an IEC version of those curves too, which is different. So if you're in outside the U.S., Europe, I think the Asia too, would tend towards using IEC type curves. Yeah, this is kind of important. Usually you try to keep the type of curve, whether it's extremely inverse or very inverse, you try to keep it the same on all your devices. But you can do, as long as your upstream stuff is less inverse, you're okay. So for an example, a very inverse relay upstream will coordinate just fine with an extremely inverse relay downstream. But the opposite's not true. So an extremely inverse relay that's downstream will conflict with a very inverse relay that's upstream. So rule of thumb is to try to keep them all the same curve type when applicable and possible. And if not, always have your less inverse curve upstream. Here's a couple little tips on coordinating with different types of fuses. If it's an expulsion fuse, you usually want to use a delayed instantaneous. If it's a current limiting fuse, you can use full instantaneous protection, no delay, and rule of thumb's about, you set that to about 110% of the current limiting value of the fuse. That gives you enough clearance time. Here, I'm promising I'm getting to the end here. Here's just I printed out some examples of in EasyPower how to set the relay. So you have your each device, you have your manufacturer. Here's your type. This one's multifunction, so you can add in as many functions as you want to have turned on in a relay. So this one's really basic. It's got a instantaneous and time over current phase. Same for the neutral, and then a time over current for the ground. And then here's the details on so you have basically kind of 4 devices in one. And then under the settings tab, this is for device number 1, is your 5051P. That's why it's called it. So you can call it whatever you want. Then you have your 51 protection. This is the range. And then, which is this one, for this case, is preset. And then you have your setting. And that's the tap value. And here's your time dial. This is where you pick the curve. Now, when you select this for this specific relay, you're going to get a whole list of curves. So I just selected the ANSI extremely inverse on this relay. Time dial setting, range. This is for your instantaneous protection. This 50 here is for your time delayed version of it, because you have a time delay plus a tap setting, and then this 50 here is for your instantaneous. So you actually have essentially what is a long time, short time, and then a true instantaneous setting all on this relay. And then here, just real quick, these are examples of modern, our current day relays, and the circles in them kind of just give you a feeling of the number of protected devices you can get all in one box. Like this is a really basic numerical relay, and you got your 50, 51, all 3 phases, plus you have ground current, neutral. This AFD is additional functions for arc flash detection. So you have basically all these devices built into one box. And then here's just a slightly more advanced relay with both a current and voltage input, but still a basic feeder relay for feeder protection. And you got a whole slew of more stuff you can do: like under voltage, over voltage, directional power flow, directional overcurrent, frequency, just tons and tons of things that you can do with a single box. And then here, lastly, I think it's the last slide. This is an example. I pulled up one of the ranges of our relays in terms of what curves you can select. So you got a whole slew of stuff. You got all your ANSI from extremely inverse down to definite time. I don't even know what ITE inverse. Honestly, I can't tell you what some of this stuff is. then your IEC curves, which is the European standard, and the same thing. You got all your inverse type things. Programmable, you can actually go in and program basically your own curve in the relay. So it's got essentially infinite flexibility on developing the kind of curve that you need for your specific protection. So I know it went a little long, but I appreciate your time. If we got a couple more minutes, I can do questions, or I can take them offline.
Andrew, you want me to read some questions to you?
Yeah, if we're good with time, I'm fine.
We got a couple minutes. So what's the difference between a type C and a type T in the CT discussion?
The type C has does not require to be tested. It can be on a its curve is by design and produced, and you can get the actual production curves for it. The T means tested. So its saturation curve is done by test.
All right. Is there a benefit or preference for having the CT before the breaker or after the breaker for relays?
Yeah, there is. It's for zone and protection. If it's a main, you'd want it on the line side. If it's a feeder, you want it on the load side, because that way your zone of protection extends a little past the breaker.
Right. And then the last question, are MV breakers typically 100% rated?
Yes. The ratings are completely different than low voltage, but yeah, they're 100% rated, with the caveat that for your particular application in terms of temperatures and whatnot, you may want to go in to look at that to make sure that you're within that rating.
Looks like our time is up. I'm sorry we didn't hear from Nikita, but I appreciate the presentation. And as I mentioned earlier, we'll have a PDF copy of the slides available when the video is posted to the website. Thank you very much. Have a good day. So long.
Thanks, everybody.
Thanks, everyone. Thanks, Jim.
Sure.